Okay, so welcome everyone. Let's get this started. So this is the seventh recitation of our CS 2100 course. And today I'll make a couple of announcements as usual, and then I'll do a review problem, which is a small proof about sets, and then we'll do some problems related to functions and relations. So that's the plan for today. And Lynn is the TA that will assist with monitoring the chat for questions and so on. So if you have any questions at any point, feel free to raise your hand, unmute yourself. There isn't that many students who are joining these days, so you can totally unmute yourself and just ask the question, or write it in the chat. Either way works. Okay, so let's get this started. So quick announcements. So we are almost done grading quiz 2. We'll release the grades tonight. And I have kind of a related announcement on the next slide that is particularly important. Then homework 4 will be out this Friday, October 9th. And quiz 3 is coming up. So it'll be on Tuesday, October 20th. As usual, you'll have 1 hour window between 7:30 a.m. and 4 p.m. on that day. So quiz 3 will be only on sets and Boolean algebra. So that's section 3 in your textbooks or lectures 8, 9, 10. So functions and relations are not going to be on quiz 3. So just sets and Boolean algebra. So you can expect some questions related to properties of sets. We solved that in the last recitation where you kind of had to say true or false for a bunch of statements based on your knowledge of properties. And some simple proofs about sets, like element-wise proofs, like the one we'll do soon. So that's the plan for quiz 3. So I want to make kind of one important announcement that I also posted on Canvas. So unfortunately, when we were grading quiz 2, we identified some instances of cheating. So after that came up, Professor Phillips and I discussed how we want to deal with this. In the syllabus, we clearly specify that whoever is caught cheating, we're going to, submit an official request to the department that the person who cheated automatically fails the whole course. And it also goes on the record and so on. So that's what we would usually do. But this semester, it's kind of a weird online semester, and COVID is happening, and it's challenging for all of us. And, I can easily see that some of you just, made a mistake and caved in and cheated. And so we wanted to be generous and give you this one opportunity to come forward and admit that you cheated by midnight tonight by sending an email to my email address. And if you do that, you will get 0 points on this quiz, but we will not fail you for the whole course. Basically, there'll be no other consequences except getting 0 points on that quiz. So I think that's really generous because, we are also dropping the lowest quiz grade. So if you do well on everything else, and this is the only mistake you make this semester, you can still do really well in the class. If you don't come forward by midnight tonight, then tomorrow, for students who don't do that and we discover that they cheated, we'll trigger the process and request that you fail the whole course. So that's the plan. Know that we're doing this only for quiz 2. Going forward, if we catch you cheating, you'll fail the whole course. Okay. So that's the important announcement I want to make. So keep this in mind. Any questions so far before we dive into solving a bunch of problems on sets, functions, and relations? Okay, good. Let's go to much more fun and pleasant stuff. And so let's solve a couple of problems. So the first one is review. It's a question of sets, and it's an element-wise proof about sets. Another quick one. So in the previous recitation, a student asked about the pigeonhole question that we had on the quiz. And it was the hardest question on the quiz. So if you struggle with that question, don't be surprised. I consider it to be the hardest one on the quiz. And so I sketched out a solution. And so, it's all recorded. You can look it up. And also Mark will make, if he didn't already, he will make an announcement kind of showing one or two kind of correct solutions for this problem. So you can look for those if you struggle with that question. Okay, but coming back to this, so we have an element-wise proof. We want to prove this fact about these sets. So we want to prove that this the union of these first two sets is a subset of this second set. So quick reminder of the element-wise proofs. If you want to prove this subset, you have to show that assuming an element A that belongs to the left-hand side, you have to prove that this same element belongs to the right-hand side as well. So the structure of the proof is, let's say, you assume that you have some element A that belongs to the left-hand side. And then we want to show that this same element belongs to the right-hand side as well. So we have A, an element of x less than -3, where x is element of R, union y greater than 3, when y is an element of R. So we assume we have such an A, and now we have to prove that A is also an element of z squared greater than 9, where z is an element of R. So how do we do this? We still have this union here. And so by this definition of union, we know that if something is an element of, x union y, then either it's an element of x or it's an element of y. So we are going to have two cases here. So we are going to have case one. So that's when A is an element of x less than -3, where x is an element of R. And we have to prove for case one that A is an element of this set z squared greater than 9. And similarly, you're going to have case two, where A is an element of y greater than 3, where y is in real numbers. Okay, so how do we prove this? So from the definition of set membership, we know that A is less than -3, and we know that A is an element of R. So this just follows from the fact that A belongs to this set. So now, from the fact that A is less than -3, we know, first we know that A plus 3 is greater than 0. So we know that by simply moving 3 to the other side. And then if we subtract 3 from both sides, we get that A minus 3 is less than -6. in less than minus 6. And from here, it follows that a minus 3 is also less than 0. So why am I doing this? So I'm keeping in mind my goal. So we want to show that a squared is greater than 9. So this is that we have to show, and we have to do the steps kind of in between to show that. So I'm looking. This also means that a squared minus 9. Sorry about this. I don't know why I might get this weirdo line often. A squared minus 9 is greater than 0. So from this fact that a is less than minus 3, somehow I have to get to a squared minus 9 is greater than 0. And so, I see, okay, there is some square here. So I somehow probably want to square a to get in this form. And that led me to this step, that a plus 3 times a minus 3 is greater than 0. So that follows from the fact that a plus 3 and a minus 3 are negative. And if you multiplication of two negative numbers, numbers is negative. Okay, so we know this, and now when we multiply it out, we get a squared minus 9 greater than 0, and from there we get a squared greater than 9, and from there we know that a is an element of z squared greater than 9, such that z is an element of R. Okay, so this shows case 1. Case 2 is very similar. Any questions about this proof of case 1?
One student asked, multiplication of 2 negative is positive, is it right?
Right. So yeah, so the multiplication of two negative numbers is always positive. Oh, sorry. Thank you for spotting this. Yeah, I have an error here. I wonder what I actually said. Did I say the same thing that I wrote, or did I say it's positive? Either way, thanks for spotting this. It's positive. Good catch, thank you. Okay, so one thing to kind of, so this is a harder element-wise proof. Usually, it kind of proving this kind of just follows in a pretty straightforward way. Here we had to do this trick on this line, on these two lines, right? I think the key is figuring out that you need something like this to be able to bridge from a less than minus 3 to a squared greater than 9. And that requires some thinking, and that's why this is a hard proof. Like, this is not an easy proof. So, keep this in mind. Now, we still need to do case 2, and I will actually leave this for you to do at home. I will put it up in my scribbles, so if you get stuck, you can actually look it up. But it's almost the same as case 1, except you will have multiplication of two positive numbers, which is also a positive number. So you'll have to reason a little bit about that, but they're almost the same. Let me just write you what you have to prove, and then we'll move ahead. So in case 2, you want to prove that if A is an element of this set y greater than 3, such that y is an element of R, you have to end up with, A is an element of z squared greater than 9, where z is an element of R. You have to fill in the middle.
Professor,
Yes.
there's a student that says there's no audios on YouTube, and I checked, there's no.
There's no audio on YouTube?
Yes, there's just one that in the next section, not this section.
I have. So what do you mean by last section? There's no audio in.
No, no live on. It's not live on YouTube for this section.
It's not live on YouTube?
Yes.
Okay. Thanks for telling me. It's funny. It should be there. I actually turned it on. So I'm not sure why it's not there. In the morning, there were some problems with YouTube streaming. What I will do is I will also record on this computer. So I started recording locally from now on. So in the worst case, I'll be able to post the video from now on. And I'm sorry it's not on YouTube. Oh, it's streaming, but there's no audio. Okay, that's even weirder. Then I have no clue why it's happening. Some people have audio. Okay, so I'm sorry. It might be some kind of weird Zoom YouTube problem. Like I said, I also turned on local, saving this locally. So there will be video, but it might not be live. So sorry about that. Okay, so let's move ahead. Finish this proof at home. Like I said, it's easy. You just follow the same structure as case 1. What do we have next? Okay, so let's do an easy question on function. On functions, and let's do breakout rooms. I think it's a good exercise. And you also get to know your peers a little bit. So it's an easy question. You want to draw an arrow diagram for this function. So I'll give you just a couple of minutes to do it. I'm streaming to the wrong YouTube channel. Okay, let's forget about YouTube and because I have to focus on this. So let's do this in breakout rooms. So you have to draw the domain and codomain. You have to connect them using an arrow diagram. So please join the rooms, and then we'll resume. And in the meantime, I can try to look up the YouTube. I guess I can do it. I can do it with my other computer. Well, it's okay.
Oh, where is it? I cannot see what is playing now. It just have the recitation for 10:45.
I don't know.
Okay, it's maybe my bad.
So let me see. Oh, let me see. I mean, I see it now. Maybe it is in the wrong channel. So maybe I stream under Zvonimir Kamaric, and that's why people cannot find it. Yeah, maybe it's that. I'll post it in chat. Okay, welcome back, everyone. So I hope this is an easier question, but I hope breakout rooms were still fun. So to kind of speed this up a little bit, I already sketched the domain and codomain. I already solved this problem once in the previous recitation, so I I learned that if I change the order a little bit, I get a little bit nicer arrow diagram. But note that for correctness, the order doesn't matter. So on the quiz, if you have to do this in whichever order you list domain and codomain, as long as your arrows are correct, you'll be fine. Okay, so domain is up, codomain is down. You can write them left and right. That's also fine. But the way the slides are laid out, this works a little bit better for me. So what is the definition? So, okay, we are mapping all elements of the power set of X to elements of the power set of X. So I listed both power sets. And the rule is that C of A is equal to X minus A. So these are all set operations. So what does empty set map to? It maps to set X minus empty set, which is just X. So empty set maps to ABC. A maps to X without A. So it maps to BC. B maps to AC. And C maps to AB. Then AB maps to set X without A and B. So that's just to C. BC, same thing, just without A. And AC then maps to B. And ABC maps to an empty set, because X minus ABC is just an empty set. So this is the arrow diagram for this function. So this should be pretty easy. This is like an easy question for a quiz. Any questions about this?
Yeah, for the C of A equals X minus A, how did you know that A refers to like the missing parts of the set X?
Okay, so good question. Let me talk about this a little bit more. So this C of A is equal to X minus A. So that's the rule for C. So maybe it's a little bit unusual because what we've usually seen, when we were writing functions was something like, f of X is equal to whatever, something like X minus 2. So this is the rule for f, and this X is the argument of f, right? And you can apply this rule on some number, and then you can compute the domain, the codomain, right? You can compute what it maps to. So the same happens here. So this is the rule for C. So I computed these arrows in my head by plugging each of these elements of the domain into this rule. So let's take one for an example. Let's take AB as an example. So to compute what AB maps to, what you have to do, you have to put this AB into this rule for C. So you do C of A comma B, and that is equal to X minus A comma B. And that is equal to X is A, B, C minus A comma B. And that is equal to C. And therefore we have an arrow from this set AB to C. So this is what you have to do for each of these elements in your top row, each of these elements on domain. So, given this is a relatively easy rule, I just did this, in my head. But if you cannot figure it out, or you need to kind of really write it out, you are more than welcome to go through this exercise that I did below for each of these elements in the domain, and then draw the arrows. So you can totally do that on the side. Like, you don't have to do it in your head. I hope this answers the question. Any other questions? Okay, so let's move to my second problem on functions, which is an easy proof about functions. So these are the sorts of proofs that we'll be doing about functions, and you can expect to have one such proof in quiz 4 as well. So what do we have? So we have g, which is a function that maps reals to reals. And the rule is that g of x is equal to 5x minus 7. And we want to prove that g is invertible. And we do this by proving that it's both one-to-one and onto. So one-to-one and onto are true properties of functions that you should be familiar with and we covered in the lectures. Okay, so how do we do this? So we have to prove two things. G is one-to-one. And we want to prove that G is onto. If we prove both of these, then we know it's invertible. So usually one-to-one is an easier proof. So let's do that one first. And in the lectures, I sketched out, we sketched out the skeleton for how we do these two kinds of proofs. So how do we do one-to-one proof? So we assume we have two elements, let's say x and y. You can use any variables you want, that are an element of the domain. So this is domain. I'll specifically note this down here because domain and codomain are the same, so to avoid confusion. So let x and y be given. So that g of x is equal to g of y. So this is how we always start one-to-one proof. And so this is, you have to assume that these two elements exist. And then, we have to do some series of steps, and we have to show that x is equal to y. So that's the skeleton of a one-to-one proof. So let's fill in the steps. Usually it's pretty easy. You plug in the rule instead of just g of x and g of y. And so you get 5x minus 7 is equal to 5y minus 7. So 7 and 7 cancel, and you get 5x is equal to 5y. And if you divide both sides by 5, you get that x is equal to y. So that concludes the one-to-one proof. Now we still have to do the onto. And this one is a little bit trickier, but we did specify how the skeleton of the proof should look like. So here you assume that you have some y element of R. In this case, this R is a codomain. And now, after we assume that, we have to show that there is some Z at this element of R, where this R is a domain. such that g of z is equal to y. So we have to fill in here the steps to show that if we pick some y in the codomain, we can find z in the domain such as g of z is equal to y. So now the main part of this proof is to figure out what this z should be. You can figure this out off the top of, just by kind of thinking. What I find useful is to have a little kind of side computation to figure out z, and we can figure it out from the rule. So we know that y should be equal to 5 times z minus 7. So from there, we can derive that z is equal to y plus 7 divided by 5. So that's a little side computation. It's not a part of the main proof. This just helps us to find what this z should be. So now in the proof, we take z to be equal to y plus 7 divided by 5. We also know we have to establish that this z is element of R, and then the g of z is equal to y. So let's first do g of z is equal to y. So let's compute g of z. G of z is equal to g of y plus 7 divided by 5, and that's equal to 5 times y plus 7 divided by 5 minus 7. We plug it into the rule. 5 and 5 cancel, and we get y plus 7 minus 7, which is just equal to y. So we show that g of z is equal to y, and we still have to show that z is an element of R. Well, we know that, let me write this down. Since y is an element of R, we know that y plus 7 divided by 5 is also an element of R. And that's because of closure of plus minus division under R. And from that, it follows that z is an element of R. Okay, so we picked some y in the codomain. Then we found z, and we specify what it is, which is an element of the domain. And we showed that g of z is equal to y, and z is an element of R. And so by doing this, we proved that g is onto. And so because we proved that it's both 1-to-1 and onto, we know it's invertible. And so this concludes the proof. So any questions about this proof?
Can you show how you were able to use closure?
So let me sketch this here in the top right corner. So we have that y plus 7 divided by 5. So that's what we are starting with, and we know that y is an element of R. So real numbers are even nicer than integers. So real numbers are closed under addition, subtraction, multiplication, and division. So they're closed under all of these operations. So if y is a real number, then we know that y plus 7 is also a real number, because 7 is a real number and real numbers are closed under addition. Sorry, and we don't need multiplication. We don't need subtraction. We just need addition and division. So if y plus 7 is a real number, and we know that 5 is a real number, then y plus 7 divided by 5 is also a real number, because real numbers are closed under division. So that's how I use closure. And we actually don't need subtraction. We just need division and addition. Any questions about this? Okay, so make sure to practice these kinds of proofs. You know, they're important, and they will be for sure on quiz 4. One thing to yeah, I think the trickiest part is to figure out what z should be. I think this side computation I did in this bubble here helps. And one-to-one proofs are usually easy. Okay, so let's move ahead. So now we have a couple of simple questions about relations. So let me do the first one for you, and then you guys can try to do the second one. So let R be the relation on set A, which contains 2, 3, 4, defined by the relation less than, which means that x is less than y. And we want to write this R as a set of ordered pairs. So, okay, so we are looking for all the pairs that we can come up with by combining elements from A, such that the first element of the pair is less than the second element of the pair. So what would these pairs be? So R is equal to 2, 3, since 2 is less than 3. What do we have? 2, 4, and 3, 4. So that's the set of ordered pairs that defines R. Any questions about this? So this is an easy one as soon as you know how to do relations. Okay. So why don't you guys try to do this one on your own? I'll give you maybe a minute or two. It's an easy one. So you want to write the inverse of the previous relation. Also as a set of pairs. And so if you remember how you do relations, inverses of relations, well, you basically just have to reverse the arrows, right? You have to go in the other direction. So you have to reverse the pairs. And you then also describe what this inverse is in words. So if R is greater than, then R to the power of minus 1 is the inverse of it. And then maybe in a minute I'll solve it for you.
Can you go back to the last slide so we can see the numbers again?
Sure. Yeah, sorry about it.
Thank you.
Okay, so let's do this. So R minus 1 is equal to, and this crazy line that always somehow comes up. I should work on resolving this. You just have to flip the pairs, right? So, okay, this is getting a little bit frustrating. Okay, I missed the whiteboard or blackboard. So what do we have? We had 2, 3. So that will become 3, 2. Then we had 2, 4. So that will become 4, 2. And we had 3, 4. So that will become 4, 3. So that's the inverse. Describe it in words. It's kind of an additional little side question. So the inverse, I would say, would be greater than equal to, if you need to describe it in words, or greater than, that would work as well. So both of these are fine. So these both describe r to the power of -1. Another kind of sub question for something like this would be to draw the arrow diagram. So we can quickly do that as well. I'll draw it vertically now. So your domain is 2, 3, 4. Your codomain is also 2, 3, 4. And so this relation maps 3 to 2. It maps 4 to 2 as well. And it maps 4 to 3. So this would be an arrow diagram for this relation. So, okay, any questions about this one? Okay. So let's do one more. And then why don't you guys try this? I'll give you 1 minute and then I'll solve it for you and then wrap it up. So here we have the relation that maps non-negative integers into non-negative integers, and it's specified by this equation where x squared plus y squared is 25. And we want to write it again as ordered pairs. So this one is kind of interesting because both domain and codomain have an unbounded number of elements. But we can still write it as a relatively small set of ordered pairs because only very few of them satisfy this equation. If you would have to draw an arrow diagram for this one, you would not be able, that would be hard because you would have to write, an unbounded number of numbers in the domain and codomain. So, but with ordered pairs, you can specify it very succinctly. Okay, so let me do this because we are running out of time. So this R is equal to, it's a set of ordered pairs. And my curly braces are horrible. I apologize for this. So their squares have to add up to 25. So we have 0, 5. We also have 5, 0. Note that these two are not the same, right? First one maps 0 to 5. The second one maps 5 to 0. So don't forget to list both of these. And then we have 4, 3 and 3, 4. So that's our R. The order doesn't matter. So the order within this parenthesis matters because these are pairs, but the order of pairs, how they're listed in this set doesn't matter. So that's the solution to this problem. Any final questions? Okay. So thank you all so much for joining in. I will figure out what happened with the video, and it will be actually posted on Canvas, so don't worry about that. Yeah, enjoy the rest of your day. Bye, everyone.
Thank you.